Erwin Schrödinger's revolutionary role in shaping quantum mechanics begins long before his name became a symbol of scientific imagination. It begins in a world where physics was standing at the edge of a cliff, looking into mysteries it could not yet describe. Classical science had explained falling apples, planetary motions, and the force of gravity with beautiful clarity, but the microscopic universe remained elusive. At this turning point stood Schrödinger, a thinker who refused to accept half answers and dared to explore regions of nature that defied logic. His contribution to quantum mechanics was not just a scientific step, it was a redefinition of how humanity understood the material world. To understand his impact, one must imagine the scientific landscape of the early 1900s. At that time, the structure of atoms was still unclear, electrons behaved in ways that contradicted expectation, and light seemed to shift between waves and particles, depending on how it was observed. Scientists like Planck and Einstein had opened the door to a new type of physics, one that suggested energy was not smooth and continuous but came in small packets. Yet these ideas were untested, uncomfortable, and incomplete. Schrödinger entered this scene with an approach that blended mathematics, philosophy, and intuition, allowing him to see what others could not. He sensed that the microscopic world required a new language, not the rigid formulas of classical mechanics, but something more flexible, something capable of describing movement, uncertainty, and duality. Schrödinger's revolutionary role began with a deep dissatisfaction with the existing models. Many scientists were trying to force quantum phenomena into classical shapes, like trying to fit the ocean into a glass. Schrödinger instead embraced the mystery. He believed that if electrons behaved strangely, the mathematical tools used to describe them must also be strange. Rather than resisting this idea, he welcomed it. This willingness to break from tradition became the seed of one of the most powerful theories in modern science. His famous wave interpretation of matter brought a new way of seeing particles. In the classical world, a particle is a point, a tiny bead moving along a defined path. But Schrödinger recognized that this certainty vanished at the quantum level. He proposed that particles should be described as waves, smooth and continuous patterns that spread out through space. This idea was radical because it implied that matter was no longer a set of solid objects, but a field of possibilities. The position of a particle could no longer be known with absolute precision, it could only be predicted through wave behavior. Schrödinger's vision reshaped physics by replacing certainty with probability, opening a path that would eventually define the entire structure of quantum theory. The creation of the wave equation, now known simply as Schrödinger's equation, marked the moment when quantum mechanics transformed from speculation into a systematic discipline. It provided scientists with a tool to calculate how particles evolve over time, where they might be found, and how they behave in different conditions. But the significance of this equation goes far beyond mathematics. It introduced the idea that the universe is not built from simple blocks of matter, but from dynamic patterns of energy, vibrating and interacting in ways that challenge human intuition. Schrödinger gave form to this invisible world, turning abstract quantum ideas into something that could be measured, tested, and explored. The development of quantum mechanics was not a solitary achievement. It was a field shaped by many minds, but Schrödinger's contribution stands apart because of its clarity and elegance. His equation offered a deep sense of order within the apparent chaos of the microscopic world. It showed that even in uncertainty, there is structure. Even in probability, there is law. Schrödinger did not simply add a new formula to physics, he created a new worldview. His work suggested that the universe operates on principles far more subtle and interconnected than classical physics ever imagined. Part of Schrödinger's revolutionary influence came from his philosophical mindset. He approached science not as a technician, but as a thinker who understood that physics and philosophy are inseparable when exploring the nature of reality. He believed that quantum mechanics was not only about particles, but about the fundamental structure of existence. His writings reveal a mind constantly asking deeper questions. What is matter? What does it mean for something to exist? How does observation shape reality? These were not side thoughts, they were central to his scientific work. Schrödinger's ability to merge mathematical precision with philosophical depth allowed him to see patterns that others overlooked. His revolutionary role also stems from the way he challenged established interpretations of quantum mechanics. While some embraced the randomness and unpredictability of the quantum world without question, Schrödinger refused to accept that nature was fundamentally chaotic. He believed that beneath the surface, there must be coherence. His wave interpretation was, in many ways, an attempt to restore continuity to physics. He did not deny uncertainty. Instead, he sought to understand its source. This pursuit led him to propose thought experiments that exposed the limitations of existing theories and forced scientists to rethink their assumptions. Schrödinger's contributions did more than solve equations. They sparked debates that shaped the philosophical foundation of modern physics. His work challenged the idea that the universe exists independently of observation, encouraging scientists to reconsider the role of consciousness in physical processes. These questions may seem mystical, but within the context of quantum mechanics, they are unavoidable. Schrödinger brought these discussions into the scientific mainstream, making them a vital part of the field's development. Another dimension of Schrödinger's revolutionary impact lies in his ability to communicate complex ideas with clarity. Many scientific pioneers generate theories that remain inaccessible, locked behind layers of technical language. Schrödinger, however, had a gift for explanation. He could describe quantum phenomena with elegance, making them understandable without sacrificing accuracy. His writings inspired generations of scientists, not because they were simple, but because they illuminated deep truths in a way that felt natural. This ability helped ensure that his ideas spread widely, influencing fields beyond physics, including biology, chemistry, and philosophy. His role in shaping quantum mechanics is also tied to his intellectual courage. At a time when new theories faced skepticism, Schrödinger stood firm in his conviction that the wave model was essential to understanding the quantum world. He was willing to challenge respected scientists, question accepted principles, and propose alternatives that seemed strange but proved accurate. This courage is part of what makes him a revolutionary figure. Scientific progress often depends on individuals who are willing to take risks, and Schrödinger took them boldly. The impact of his work extended far beyond his lifetime. Today, quantum mechanics powers technologies such as lasers, transistors, semiconductors, and quantum computers. All of these rely on mathematical tools that trace their origins back to Schrödinger's insights. His equation forms the backbone of modern physics, used daily by scientists around the world. It guides research in fields such as quantum chemistry, material science, and particle physics. Without Schrödinger's contributions, the technological world we know today would look entirely different. Even more profound is the way Schrödinger changed humanity's perception of reality. He showed that the world is not a collection of separate objects, but a seamless web of interactions. Particles do not exist in isolation. They are part of patterns that transcend classical boundaries. This idea has influenced not only science but also philosophy, pushing thinkers to reconsider the relationship between mind, matter, and the universe. Schrödinger invited people to see nature not as a machine but as a dynamic, interconnected system full of mystery and depth. His revolutionary role is recognized not because he provided all the answers, but because he expanded the range of questions. He taught scientists to embrace uncertainty, to look beyond the visible, and to explore the fundamental principles that govern existence. Schrödinger's work illuminated a new world, one that continues to challenge and inspire. He did not simply shape quantum mechanics, he shaped the way humanity understands knowledge itself. Schrödinger's revolutionary influence becomes even clearer when one examines the deeper effects of his work on the scientific mindset. Before his ideas took hold, physics was a discipline rooted in certainty. Measurements, forces, and trajectories were treated as absolute truths that could be predicted with perfect accuracy if enough information was known. Schrödinger helped dismantle this confidence by showing that nature, at its smallest scales, does not behave like a clockwork machine but like a fluid, ever-shifting landscape where probability rules. His contributions forced scientists to accept that the universe contains layers of complexity far beyond human intuition. Yet instead of seeing this as a limitation, Schrödinger saw beauty in it. His work brought a profound sense of wonder to physics, reminding humanity that mystery is not a barrier, but an invitation to explore deeper. The world he helped build through his equation is one where particles occupy multiple possibilities at once, where reality emerges from mathematical waves, and where the act of observation plays a defining role in shaping the outcome. Without this understanding, modern physics would be incomplete. Schrödinger's role in establishing this perspective was not merely technical, it was philosophical. He encouraged scientists to question not only how nature behaves, but why it behaves that way. His writings invite readers to confront the idea that the universe is not a fixed stage, but a dynamic process unfolding in ways that challenge everyday logic. In doing so, he redefined what it means to study nature. A powerful part of Schrödinger's impact comes from the intellectual landscape he influenced. After the introduction of his wave equation, the study of atoms transformed from theoretical speculation into a precise and calculable science. For the first time, researchers could predict the energies of electrons inside atoms, determine how they bond to create molecules, and understand why matter has the properties it does. This shift was monumental. Chemistry, which had relied on empirical rules and observation, suddenly gained a rigorous theoretical foundation rooted in quantum mechanics. Schrödinger's work became the bridge between the invisible world of atoms and the tangible reality of everyday materials. The periodic table, chemical reactions, and the structure of matter all began to make deeper sense through the lens of his equation. The historical importance of this transformation cannot be overstated. Entire industries, from electronics to energy production, depend on principles that trace directly back to Schrödinger's insights. When engineers design semiconductors, the building blocks of all modern digital devices, they rely on the mathematical relationships derived from quantum wave behavior. When scientists explore superconductors, quantum dots, or nanotechnology, they are using tools that Schrödinger helped create. Even medicine benefits from his contributions, as techniques such as MRI scans rely on quantum principles. Schrödinger's work is not confined to textbooks, it surrounds humans in nearly every aspect of modern life. Yet, despite this enormous influence, Schrödinger never saw himself merely as a physicist solving equations. He saw himself as an explorer navigating the edge between the known and the unknown. This is evident in the way he questioned the meaning of measurement in quantum mechanics. While others accepted that particles exist in uncertain states until observed, Schrödinger was troubled by the implications. His famous cat thought experiment was designed not to mystify, but to highlight the absurdity of applying quantum rules to everyday objects. By imagining a cat existing in a state between life and death until someone opens a box, he exposed a deep gap in scientific understanding. This thought experiment became one of the most iconic examples of scientific philosophy, illustrating the tension between mathematical theory and physical reality. Schrödinger's willingness to confront these tensions head-on demonstrates the depth of his influence. His revolutionary role also emerges through the legacy of questions he left behind. Schrödinger believed that science could not ignore the role of consciousness. He suggested that the observer is not simply a passive witness, but part of the phenomenon being observed. Though controversial, this idea continues to shape discussions in quantum theory, neuroscience, and philosophy. Schrödinger inspired countless thinkers to consider how mind and matter interact, whether observation is a physical act or a psychological event, and whether reality exists independently of experience. His contributions extend beyond equations into the foundations of how humans perceive themselves and the world around them. Another profound aspect of Schrödinger's role in quantum mechanics is the way he brought unity to a fragmented field. Early quantum theory had multiple competing interpretations, each describing nature in a different way. Schrödinger's wave mechanics offered a coherent and elegant framework that helped bring order to this intellectual chaos. His vision of particles as waves allowed scientists to apply classical intuition in a new context, making the unfamiliar quantum world more accessible. Even though other interpretations eventually gained prominence, Schrödinger's work remains central because it provides a clear and consistent mathematical structure. His approach laid the foundation for modern quantum engineering, where wave functions and probability densities guide real-world applications. Schrödinger's revolutionary power lies partly in the contrast between simplicity and depth in his ideas. His equation is mathematically concise yet capable of describing vast and complex systems. This combination allowed physicists to model atoms, molecules, and even large structures with surprising accuracy. The precision of quantum predictions raised the scientific standard, pushing researchers to refine experiments and develop new technologies to test the theory's implications. Schrödinger's work became the benchmark against which future discoveries were measured. The accuracy with which quantum mechanics describes nature remains one of the greatest achievements in the history of science, and Schrödinger is one of the central figures responsible for this triumph. Yet his legacy extends far beyond physics laboratories. Schrödinger inspired countless writers, artists, and thinkers who saw in his work a metaphor for the complexity of human experience. The idea that reality exists as a set of possibilities, shaped by observation, has influenced literature, film, and popular culture. Concepts derived from his work appear in discussions about free will, consciousness, and the nature of existence. Schrödinger's influence reaches into areas of human thought that he likely never imagined, which is a hallmark of truly revolutionary ideas. When a scientific insight becomes a cultural symbol, its impact becomes enduring. At the heart of Schrödinger's revolutionary role is his belief that science must remain open to new interpretations. He refused to let tradition or authority dictate what could be considered true. This attitude encouraged younger scientists to question assumptions and explore unconventional ideas. Schrödinger showed that progress comes not from accepting the world as it is presented, but from challenging the boundaries of understanding. His career exemplifies the power of intellectual freedom, a lesson that continues to inspire researchers across disciplines. The story of Schrödinger's contribution to quantum mechanics is also a story of human perseverance. His journey was marked by doubt, disagreement, and competing theories. Many of his contemporaries did not immediately accept his wave mechanics. Some argued that it was too mathematical, others that it lacked physical meaning. But Schrödinger persisted because he believed in the clarity and beauty of his ideas. This determination ultimately changed the direction of physics. His success shows that groundbreaking ideas often face resistance before they become accepted truths. Schrödinger's experience reminds scientists that innovation requires courage as well as insight. His impact on quantum theory also highlights the importance of interdisciplinary thinking. Schrödinger moved fluidly between physics, mathematics, philosophy, and biology. He believed that knowledge should not be confined to rigid categories. This ability to draw connections across fields enriched his scientific work and allowed him to perceive patterns invisible to others. His later explorations into the nature of life, though separate from his quantum research, reflect the same curiosity that fueled his wave equation. Schrödinger saw the universe as a continuous tapestry, with each thread connected to the next. This holistic approach continues to shape scientific thought today, especially in fields that blend physics with biology or information theory. From a modern perspective, Schrödinger's role in shaping quantum mechanics appears even more remarkable. The technologies that define contemporary life, computers, communication systems, medical imaging, and emerging quantum networks, are all built on principles that his work helped establish. Even the concept of a quantum computer, which aims to harness the power of superposition and entanglement, is rooted in the mathematical structures developed through Schrödinger's insights. His influence extends into the future, shaping discoveries that have yet to be made. As scientists continue to explore quantum gravity, dark matter, and the unification of forces, Schrödinger's ideas remain foundational. Perhaps the most powerful testament to Schrödinger's revolutionary role is the continuing relevance of his questions. What is the nature of reality? Does observation create outcomes, or merely reveal them? Is the universe fundamentally deterministic or inherently probabilistic? These are questions that physicists still wrestle with today. Schrödinger's work ensures that these questions remain alive, driving scientific progress and philosophical reflection. His influence persists because he did not merely offer solutions, he opened avenues for exploration that remain rich with possibility. In the end, Schrödinger's contribution to quantum mechanics is best understood as a transformation of human understanding. He turned invisible waves into the architecture of reality, uncertainty into a scientific principle, and philosophical curiosity into a driving force of discovery. His ideas continue to ripple through time, shaping the way humanity interprets the universe. Schrödinger stands as a figure who did not simply participate in the evolution of physics, but accelerated it, expanded it, and elevated it to new heights. His revolutionary role is not confined to the past. It lives on in every experiment that probes the quantum world and in every mind that dares to question the mysteries of existence. Erwin Schrödinger's introduction of the wave equation stands as one of the most transformative achievements in the history of science. It was not merely a mathematical development, it was a conceptual revolution that fundamentally altered humanity's understanding of the microscopic universe. At the beginning of the 20th century, physics was grappling with phenomena that defied the principles of classical mechanics. Atoms, once thought to be simple indivisible units, revealed an astonishing complexity. Electrons did not orbit the nucleus in neat, predictable paths as once imagined, and light exhibited properties that seemed contradictory, behaving sometimes as particles, sometimes as waves. Physicists found themselves in a domain of paradox where traditional formulas failed to capture reality. In this turbulent intellectual landscape, Schrödinger's insight provided a path through uncertainty, a framework that brought order and predictive power to the strange behavior of matter. The essence of the wave equation lies in its ability to describe the behavior of quantum particles in a way that accounts for their dual nature. Before Schrödinger, the emerging quantum theories, particularly those of Bohr and Heisenberg, provided glimpses of atomic phenomena but were often fragmented and difficult to apply to complex systems. Bohr's model of the atom offered discrete energy levels for electrons, but it did not explain why these levels existed or how electrons transitioned between them. Heisenberg's uncertainty principle highlighted the limits of knowledge about a particle's position and momentum, yet it lacked a clear, unifying picture. Schrödinger's genius was to propose that the behavior of particles could be understood through wave functions, mathematical objects that represent the probabilities of a particle's properties and locations. In this way, he transformed the conceptual landscape of physics, turning fragmented ideas into a coherent framework. His wave equation, introduced in 1926, offered more than a theoretical curiosity. It provided a practical tool for calculating and predicting atomic behavior with unprecedented precision. The equation describes how the quantum state of a system evolves over time, enabling scientists to predict the probability of finding a particle in a particular location or with a particular energy. Unlike classical physics, which sought absolute certainty, the wave equation embraced probability as a fundamental feature of nature. It revealed that matter is not composed of fixed points, but of dynamic patterns that shift and interfere like waves in water. This perspective challenged the very foundations of physics, requiring scientists to think in terms of probability amplitudes rather than deterministic trajectories. Schrödinger's work gave form to an invisible world, creating a bridge between abstract mathematics and observable reality. The wave equation's impact was immediate and far-reaching. It enabled scientists to calculate the energy levels of hydrogen with remarkable accuracy, solving problems that had perplexed physicists for decades. The predictive power of the equation validated quantum theory and demonstrated that mathematics could illuminate phenomena previously considered inscrutable. Beyond hydrogen, Schrödinger's approach provided a framework for understanding more complex atoms, molecules, and chemical bonds, laying the foundation for quantum chemistry. His work allowed chemists and physicists to predict molecular structures, bond strengths, and reaction dynamics with precision, connecting the microscopic behavior of particles to the macroscopic properties of matter. This practical application demonstrated that his equation was not a theoretical abstraction, but a transformative tool with real-world significance. Schrödinger's wave mechanics also introduced a profound conceptual shift in how scientists think about reality. In classical mechanics, objects are discrete and localized. In Schrödinger's formulation, particles are represented by wave functions that extend across space. This means that the behavior of a particle is not confined to a single point, but is distributed as a pattern of probability. The wave equation captures this fluidity, showing how particles interact, interfere, and evolve over time. Schrödinger's insight revealed a universe in which certainty is replaced by probability, where observation plays a critical role in defining outcomes. This conceptual leap opened the door to new interpretations of quantum phenomena, influencing the philosophical understanding of reality itself. The introduction of the wave equation also highlighted Schrödinger's ability to merge mathematical precision with intuitive insight. He recognized that the complex behavior of particles could be captured in elegant mathematical expressions without losing physical meaning. His formulation of the equation was both rigorous and accessible, allowing it to be widely adopted by the scientific community. The clarity of his approach contrasted with other quantum theories of the time, which were often abstract, symbolic, or limited to specific cases. Schrödinger's wave mechanics provided a unifying principle, capable of describing a vast range of phenomena within a single framework. This universality contributed to its rapid acceptance and enduring relevance. Beyond physics, Schrödinger's wave equation inspired a broader reconsideration of scientific methodology. By treating probability as fundamental, the equation challenged the assumption that nature could be understood solely through deterministic laws. It demonstrated that unpredictability is not a flaw in measurement or understanding, but an intrinsic property of the universe at small scales. This insight influenced the way scientists design experiments, interpret data, and conceptualize the nature of reality. Schrödinger's work encouraged a mindset that embraces uncertainty as a source of insight rather than a limitation, opening the door to the rich, counterintuitive world of quantum phenomena. The technical elegance of the wave equation cannot be overstated. It combines partial differential equations with boundary conditions to describe the evolution of quantum systems. Each solution to the equation corresponds to a possible state of the system, with the magnitude squared of the wave function representing the probability of observing the system in that state. This framework allows for the precise modeling of atoms, molecules, and even solids, bridging the gap between theory and experiment. Schrödinger's approach provided a systematic way to predict the outcomes of experiments, guiding the development of spectroscopy, quantum optics, and condensed matter physics. His equation became a fundamental tool for scientists seeking to explore the microscopic world. Schrödinger's wave equation also played a pivotal role in advancing quantum theory by offering an alternative to matrix mechanics, developed by Heisenberg, Born and Jordan. While matrix mechanics was powerful, It was abstract and lacked intuitive visualization. Schrödinger's formulation, by contrast, allowed physicists to see the behavior of particles as waves in space and time. This visualizability made quantum mechanics more approachable and easier to apply to real-world problems. It enabled scientists to perform calculations that explained phenomena such as atomic spectra, chemical bonding, and tunneling effects. By providing a concrete mathematical representation, Schrödinger bridged the gap between abstract theory and observable consequences. The broader implications of the wave equation extend beyond the laboratory. Schrödinger's insight challenged humanity to reconsider the nature of matter, energy, and the universe itself. By framing particles as waves, he introduced a perspective in which the classical idea of a particle as a localized object is replaced by a richer, more complex reality. This perspective influenced not only physics but also philosophy, prompting questions about observation, reality, and the role of consciousness. Schrödinger's equation became a symbol of a new scientific worldview, one in which certainty is limited, patterns emerge from probabilities, and the universe is understood as a dynamic, interconnected system. Schrödinger's introduction of the wave equation also directly influenced subsequent discoveries and technological developments. Quantum chemistry, solid-state physics, and nuclear physics all rely on the principles embedded in his formulation. Modern electronics, lasers, and semiconductors are applications of quantum mechanics, which in turn depends on the predictive power of the wave equation. Even the emerging field of quantum computing relies on principles derived from Schrödinger's insights, particularly the concept of superposition and the probabilistic nature of quantum states. His work laid the foundation for a scientific revolution that continues to unfold, shaping both technology and theoretical understanding. Another key aspect of the wave equation's significance lies in its elegance and simplicity. While it captures extraordinarily complex phenomena, the underlying mathematical form is concise and clear. This elegance reflects Schrödinger's belief that the laws of nature are not only true but also beautiful. He demonstrated that deep insights can be conveyed through relatively simple expressions, a lesson that has influenced generations of physicists. The clarity and accessibility of his formulation contributed to its widespread adoption and enduring impact, allowing it to become a central tool in both research and education. The introduction of the wave equation also reshaped the training of physicists. Students and researchers now had a unified framework for understanding atomic and subatomic phenomena. The wave function became a central concept, and the methods of solving Schrödinger's equation became essential skills for anyone entering the field. This standardization helped consolidate quantum mechanics as a coherent discipline and facilitated the rapid growth of the field. Schrödinger's work did not merely solve specific problems, it structured the entire way physicists approach the study of the microscopic world. Finally, the introduction of the wave equation exemplifies Schrödinger's ability to combine innovation with rigor. He took an abstract concept, the wave nature of matter, and translated it into a mathematical form that was precise, testable, and profoundly useful. His work provided both insight and utility, bridging theory and experiment in a way that few scientific contributions achieve. The wave equation remains central to physics nearly a century later, a testament to the depth, clarity, and transformative power of Schrödinger's genius. It changed the trajectory of science, reshaping our understanding of reality and laying the groundwork for the technological advances and theoretical discoveries that define the modern world. The wave equation introduced by Schrödinger was not only a tool for calculation, but also a lens through which the universe could be viewed in a completely new way. Before his work, particles were conceived as tiny, solid objects following deterministic paths, their motions predictable with sufficient information. Schrödinger's insight revealed a different reality at the quantum level. Particles behave as both waves and particles, existing in multiple potential states until observed. This duality challenged centuries of classical intuition and forced physicists to reconsider the very meaning of matter. Schrödinger provided the mathematics to navigate this strange world, showing that the probability distribution described by a wave function is not a limitation, but a fundamental characteristic of nature. Through this lens, the universe became a dynamic, probabilistic landscape, one that could be explored and understood with a precision that had previously seemed impossible. The broader scientific impact of the wave equation is evident in its ability to explain phenomena that had remained mysterious for decades. Atomic spectra, for instance, had perplexed scientists since the 19th century, while the Bohr model offered a partial explanation by quantizing electron orbits. It lacked a rigorous theoretical foundation and could not be generalized to more complex atoms. Schrödinger's equation allowed for precise calculation of energy levels in atoms, predicting spectral lines with remarkable accuracy. This achievement validated the core principles of quantum mechanics and established wave mechanics as a central framework for understanding atomic and molecular systems. It provided a unifying principle, connecting observations in physics, chemistry, and spectroscopy, and demonstrating that the microscopic world could be described with mathematical rigor. The equation also played a critical role in bridging the gap between abstract theory and observable reality. The wave function describes a system state at any given time, yet its square magnitude provides a direct link to measurable probabilities. This connection between mathematics and experiment was revolutionary. It allowed scientists to make predictions that could be tested, refined, and applied in practical contexts. Schrödinger's work transformed quantum mechanics from a collection of conceptual ideas into a predictive and experimental science. Experiments involving electron diffraction, tunneling, and molecular structures all relied on the principles embedded in the wave equation, cementing its central role in modern physics. One of the most profound consequences of Schrödinger's wave equation is its influence on the conceptual understanding of reality. The classical notion of a particle as a localized entity was replaced with the idea of a wave function spread across space. This fundamentally changed how scientists thought about the nature of matter. The universe at the microscopic scale is no longer a collection of discrete objects with fixed properties, but a complex network of probabilities and interactions. Schrödinger's equation captures this fluidity, providing a mathematical framework in which uncertainty is not an obstacle, but an intrinsic aspect of nature. By embracing this probabilistic worldview, scientists were able to reconcile seemingly contradictory phenomena and develop a coherent understanding of the quantum realm. The technical elegance of the wave equation contributed to its enduring impact. Schrödinger formulated it as a partial differential equation, a concise expression that encodes the dynamics of quantum systems. Solutions to the equation, wave functions, represent the possible states of a system, each associated with a probability of occurrence. The clarity and universality of this approach allowed it to be applied to a wide range of problems, from single electrons in a hydrogen atom to complex molecules and solids. This versatility made the equation a foundational tool in multiple scientific disciplines, including quantum chemistry, condensed matter physics, and nuclear physics. Schrödinger's innovation demonstrated that a single mathematical framework could unify diverse phenomena under a consistent set of principles. Schrödinger's wave mechanics also offered a compelling alternative to matrix mechanics, developed by Heisenberg, Born, and Jordan. While matrix mechanics was mathematically rigorous, it lacked the intuitive visual representation provided by Schrödinger's approach. Wave mechanics allowed scientists to conceptualize the behavior of quantum systems as patterns evolving over space and time, providing insight into phenomena such as interference, tunneling, and energy quantization. This visualizability facilitated understanding, teaching, and further research, making quantum mechanics more accessible to both physicists and chemists. The complementarity of wave mechanics and matrix mechanics ultimately strengthened the field, as both approaches were later shown to be mathematically equivalent, Yet wave mechanics offered an interpretive clarity that has endured. Beyond physics, the wave equation influenced scientific thought more broadly, encouraging a shift in the way reality itself is conceptualized. The idea that outcomes are fundamentally probabilistic challenged deterministic worldviews that had dominated science for centuries. Schrödinger's work suggested that uncertainty is not merely a reflection of human ignorance, but a property inherent to nature. This insight had implications beyond physics, influencing philosophy, biology, and even the nascent field of cognitive science. Schrödinger himself explored these ideas in his writings on life and consciousness, demonstrating the interconnectedness of his scientific and philosophical thinking. By presenting a universe governed by probability waves, he prompted humanity to reconsider the relationship between observation, knowledge, and reality. The introduction of the wave equation also transformed scientific methodology. Experiments were no longer interpreted solely in terms of deterministic cause and effect. Instead, probabilities and statistical distributions became central to analysis. This shift enabled the development of powerful techniques for investigating atomic and molecular systems, including spectroscopy, electron microscopy, and quantum chemistry calculations. Schrödinger's work provided the mathematical and conceptual foundation for these tools, showing that predictive accuracy and experimental validation could coexist with a fundamentally probabilistic description of nature. The wave equation thus bridged the gap between abstract theory and practical experimentation, influencing the entire scientific enterprise. The influence of Schrödinger's wave mechanics extended into technological development, underpinning innovations that define modern life. The design of semiconductors, lasers, and superconductors relies on the principles of quantum mechanics, which in turn are grounded in the wave equation. Quantum chemistry, which enables the prediction of molecular properties and reactions, depends on solving Schrödinger's equation for multi-electron systems. Even cutting-edge developments in quantum computing are directly informed by the probabilistic and superpositional nature of quantum states described by his formulation. Schrödinger's work transformed theoretical insight into technological capability, demonstrating the profound practical impact of his abstract mathematical innovations. The conceptual elegance of the wave equation is matched by its ability to unify disparate phenomena. It allows physicists to describe bound systems, free particles, harmonic oscillators, and potential wells within the same framework. This universality is one reason the equation remains central to quantum mechanics nearly a century after its introduction. By providing a single, coherent formalism, Schrödinger enabled scientists to connect phenomena across scales and disciplines. The wave equation is not merely a tool for understanding electrons and atoms, it is a foundational principle that governs the behavior of matter itself. Schrödinger's insight also emphasized the interplay between mathematics and physical reality. He demonstrated that abstract mathematical structures could capture the essence of natural processes, offering predictive power and explanatory depth. The wave equation illustrates that elegant mathematics can reveal hidden patterns in the universe, turning apparent chaos into comprehensible structure. This principle has guided generations of physicists and mathematicians, shaping the way scientific theories are developed and tested. Schrödinger's work exemplifies the power of combining imagination with rigorous mathematical reasoning to uncover fundamental truths. Furthermore, the introduction of the wave equation reshaped education in physics and chemistry. The concept of the wave function became central to curricula, providing students with a framework to understand atomic and molecular systems. The techniques for solving Schrödinger's equation became essential tools, forming the backbone of training for generations of scientists. By establishing a unifying theoretical foundation, Schrödinger influenced the pedagogy of quantum mechanics, ensuring that his ideas would propagate through scientific institutions and shape the development of future research. Another critical aspect of Schrödinger's contribution is the philosophical resonance of the wave equation. It embodies the tension between determinism and probability, observation and reality, certainty and uncertainty. These themes have inspired not only physicists but also philosophers, writers, and thinkers across disciplines. Schrödinger's work illustrates that science is not merely about describing the world, but about challenging assumptions, expanding perspectives, and inspiring new ways of thinking. The wave equation is a symbol of intellectual courage, a testament to the transformative power of questioning deeply held notions and embracing the unfamiliar. The practical applications of the wave equation are vast and continue to expand. In quantum chemistry, it allows for the prediction of chemical reactions, molecular structures, and electronic properties. In condensed matter physics, it explains the behavior of electrons in solids, giving rise to semiconductors, superconductors, and magnetic materials. In nuclear physics, it guides the understanding of particle interactions and decay processes. Even in astrophysics, principles derived from Schrödinger's equation inform models of stellar behavior and particle interactions in extreme environments. His contribution is not confined to one domain, it underpins the modern understanding of matter at every scale. Schrödinger's introduction of the wave equation also set the stage for future theoretical innovations. Quantum field theory, quantum electrodynamics, and quantum information science all build upon the mathematical foundations he established. By formalizing the wave nature of particles, Schrödinger enabled the exploration of phenomena that were once considered beyond human comprehension. His work expanded the horizons of physics, providing a framework that accommodates both the smallest particles and the largest structures in the universe. In this way, Schrödinger's wave equation is not only a cornerstone of quantum mechanics, but a gateway to the broader understanding of the natural world. Finally, the enduring significance of Schrödinger's wave equation lies in its combination of practical utility, conceptual clarity, and philosophical depth. It provides a precise method for calculation, a coherent model for understanding matter, and a lens through which the nature of reality can be questioned and explored. Schrödinger's formulation exemplifies the fusion of imagination, rigor, and insight that defines revolutionary scientific achievement. Nearly a century after its introduction, the wave equation continues to shape scientific thought, guide experimental discovery, and inspire philosophical reflection. It stands as a testament to the transformative power of one mind, daring to see the invisible patterns of the universe and translate them into enduring knowledge. Erwin Schrödinger's bold questioning of physical reality through thought experiments marked a turning point in the way scientists approached the mysteries of the quantum world. At a time when the foundations of physics were shifting beneath their feet, Schrödinger was not content to accept established interpretations without scrutiny. Quantum mechanics was emerging as a powerful framework for describing the subatomic world, yet its predictions often defied intuition and challenged the basic assumptions about nature. Particles seemed to exist in multiple states simultaneously, energy appeared quantized, and observation itself played a critical role in determining outcomes. Amid this uncertainty, Schrödinger sought clarity not merely through equations, but through imaginative experiments that could reveal the implications of quantum theory in ways that were conceptually graspable. Thought experiments have a long history in science, but Schrödinger used them with extraordinary sophistication and precision. He understood that equations alone could describe the world, yet they could not communicate the paradoxes embedded in quantum mechanics to a broader audience. His experiments were not meant to be physically executed in a laboratory, rather, they functioned as intellectual probes, tools to stretch the imagination and illuminate the hidden consequences of theory. Schrödinger's approach demonstrated that the act of questioning, posing hypothetical scenarios and examining their logical outcomes, could be as revealing as experimentation itself. By pushing theoretical physics into the domain of thought, he created a method for exploring questions that were otherwise inaccessible, allowing scientists to grapple with the philosophical as well as the mathematical dimensions of quantum mechanics. Central to Schrödinger's use of thought experiments was the challenge of reconciling the mathematical formalism of quantum mechanics with the everyday experience of reality. Classical physics described a world of solid objects moving predictably through space and time. Electrons, photons, and atoms, however, did not conform to these intuitive rules. Schrödinger recognized that quantum theory suggested phenomena so counterintuitive that mere mathematical statements could fail to convey their strangeness. In response, he designed scenarios that made these abstract principles tangible. By translating probabilistic wave functions into relatable images, Schrödinger provided a bridge between the incomprehensible behavior of the microscopic world and human cognitive understanding. His thought experiments acted as conceptual microscopes, revealing the structure and paradoxes of quantum theory in a form accessible to both scientists and thinkers from other disciplines. Perhaps the most famous example of Schrödinger's approach is the scenario involving a cat placed in a box with a mechanism linked to a quantum event. In this experiment, a particle's probabilistic decay determines whether a poison is released, leaving the cat simultaneously alive and dead until the box is opened. While the scenario is hypothetical, it crystallizes a profound question. How do the strange rules of quantum mechanics apply to the macroscopic world we inhabit? The experiment highlights the conflict between quantum superposition, in which a system exists in multiple states simultaneously, and classical reality, in which objects occupy definite states. Schrödinger's cat became more than an illustration. It became a symbol of the tension between mathematical theory and observed experience. It forced scientists to confront a critical question: does the universe behave differently when observed, or does observation merely reveal what is already determined? Through this bold questioning, Schrödinger challenged not only the content of quantum mechanics, but also the underlying assumptions of reality itself. The significance of Schrödinger's thought experiments extends beyond their illustrative power. They catalyzed rigorous discussions and debates among physicists about the interpretation of quantum mechanics. The paradoxes he presented highlighted the limitations of prevailing theories, forcing scientists to consider alternative perspectives. Questions about the role of the observer, the completeness of quantum descriptions, and the nature of measurement became central to the development of the field. Schrödinger's intellectual provocations contributed directly to the formulation of competing interpretations of quantum mechanics, such as the Copenhagen interpretation and later developments in many worlds theory. By pushing the boundaries of conceptual understanding, he shaped not only the technical progress of physics, but also its philosophical evolution. Schrödinger's approach to thought experiments also illustrates his distinctive intellectual style, which combined mathematical rigor with imaginative speculation. He was comfortable moving between precise calculations and bold conceptual leaps, using hypothetical scenarios to test the implications of equations in ways that pure computation could not achieve. This dual approach allowed him to explore both the formal structure of quantum mechanics and its broader meaning. His ability to operate at the intersection of abstract theory and intuitive reasoning made his work influential, not only within physics but across scientific and philosophical communities. Schrödinger demonstrated that creativity and logic are not opposed but complementary tools in the pursuit of understanding. Another key aspect of Schrödinger's questioning is its focus on the paradoxical nature of quantum phenomena. He recognized that conventional notions of causality, locality, and determinism were inadequate at the microscopic scale. By imagining situations in which these principles were put to the test, he highlighted the counterintuitive reality of quantum mechanics. These paradoxes were not intellectual games, they were essential tools for exploring the limits of scientific knowledge. Schrödinger's boldness lay in his willingness to confront the uncomfortable implications of theory rather than smoothing over inconsistencies or ignoring anomalies. In doing so, He demonstrated that progress in science often requires confronting uncertainty and embracing conceptual challenges. Schrödinger's thought experiments also reveal his deep concern with the philosophical implications of science. He did not view physics as a purely technical endeavor, but as a means of understanding the nature of existence. By designing experiments that challenged the boundary between the microscopic and microscopic worlds, he raised fundamental questions about reality, observation, and knowledge. These questions extend beyond physics, touching on metaphysics, epistemology, and the philosophy of mind. Schrödinger's work thus exemplifies the intersection of scientific inquiry and philosophical reflection, showing that the pursuit of understanding cannot be confined to equations alone. The practical influence of Schrödinger's conceptual probing is evident in the way it shaped subsequent research. His emphasis on the observer, measurement, and superposition informed both experimental design and theoretical development. Techniques in quantum optics, quantum information, and quantum computing often rely on principles illuminated by his thought experiments. The conceptual clarity provided by these experiments guides the interpretation of experimental results, particularly in situations where counterintuitive behavior emerges. Schrödinger's method of questioning reality through hypotheticals became a template for approaching complex quantum problems, demonstrating that imagination can be as crucial as calculation in advancing knowledge. Furthermore, Schrödinger's bold questioning inspired a culture of critical reflection within the scientific community. By highlighting the limits and paradoxes of quantum mechanics, he encouraged scientists to examine foundational assumptions rather than accepting theory at face value. This approach nurtured a generation of physicists who were willing to explore alternative frameworks, challenge orthodoxy, and engage deeply with the conceptual underpinnings of their work. Schrödinger's influence thus extends beyond his specific contributions. It encompasses the intellectual environment he helped cultivate, one in which questioning and creativity are central to scientific progress. Schrödinger's thought experiments also demonstrate the interplay between theory and pedagogy. By presenting complex quantum principles through imaginative scenarios, he made the ideas accessible to students, researchers, and the broader public. His approach helped demystify quantum mechanics, showing that even the strangest phenomena could be understood conceptually, if not intuitively. This educational impact is enduring, as Schrödinger's scenarios continue to be used in classrooms, lectures, and popular science writing to convey the counterintuitive nature of quantum reality. Through these narratives, he not only advanced scientific knowledge, but also shaped the way generations of learners engage with quantum theory. The use of hypothetical scenarios to explore reality also reflects Schrödinger's commitment to intellectual rigor. He did not create thought experiments as mere illustrations. Each scenario was carefully constructed to expose specific implications of theory and highlight potential inconsistencies. By subjecting quantum mechanics to such conceptual stress tests, he strengthened the discipline, revealing areas that required clarification and refinement. His method demonstrates that rigorous scientific inquiry can encompass both abstract reasoning and imaginative exploration, showing that questioning reality is a legitimate and powerful tool for discovery. Schrödinger's work in this area also had profound implications for the philosophy of science. By illustrating the paradoxes inherent in quantum mechanics, he challenged assumptions about determinism, causality, and the nature of existence. The questions he posed about the role of the observer, the status of unmeasured states, and the limits of knowledge remain central to debates in the philosophy of physics. Schrödinger's thought experiments serve as a bridge between scientific theory and philosophical inquiry, demonstrating that understanding the universe requires engagement with both calculation and contemplation. The significance of Schrödinger's bold questioning is further seen in its influence on contemporary quantum research. Experimental techniques, from quantum entanglement studies to tests of Bell's inequalities, often trace their conceptual roots to the paradoxes he highlighted. By imagining scenarios that expose contradictions or unexpected consequences, he set the stage for experiments designed to probe the fundamental nature of reality. Schrödinger's thought experiments remain a touchstone for both theorists and experimentalists, providing a framework for conceptual clarity in an area of science where intuition often fails. Finally, Schrödinger's approach exemplifies the role of imagination in scientific advancement. He demonstrated that questioning reality is not a distraction from mathematics or experiment, but an essential part of discovery. By pushing the boundaries of thought, he revealed deeper truths about the quantum world and inspired others to do the same. His bold questioning continues to resonate, reminding scientists and thinkers that the pursuit of knowledge involves both the mind's creativity and its capacity for rigorous analysis. Schrödinger's thought experiments remain enduring symbols of intellectual courage, illustrating the power of imagination to illuminate the fundamental structure of reality. The depth of Schrödinger's contribution through thought experiments becomes even more apparent when one considers the broader implications for both science and philosophy. His scenarios were never mere intellectual exercises. They were deliberate attempts to probe the logical consequences of the mathematical formalism of quantum mechanics. By constructing experiments in the mind, he could explore situations that would have been impossible or impractical to test physically, yet the conclusions drawn from them illuminated real issues with theory and interpretation. Schrödinger's methodology demonstrated that the human imagination, guided by logic and rigor, could be as powerful a tool for understanding nature as any laboratory apparatus or mathematical technique. In this sense, his thought experiments were as much about refining human understanding as they were about testing physics itself. The famous cat paradox, often simplified in popular accounts, reflects the extraordinary precision with which Schrödinger crafted his questions. He was not advocating for literal experiments on animals, but rather illustrating the consequences of applying quantum principles universally, even to macroscopic systems. The scenario forces an unavoidable confrontation with the peculiar nature of quantum superposition, where systems can exist in multiple states simultaneously until measured. By framing the paradox in an accessible, almost narrative form, Schrödinger transformed abstract mathematics into a conceptual framework capable of being analyzed, debated, and understood. This approach highlights his genius. He translated counterintuitive phenomena into images and stories that retain their scientific rigor while communicating profound implications about reality. One of the key outcomes of Schrödinger's thought experiments was the stimulation of debate regarding the nature of measurement in quantum mechanics. Classical measurement assumes that the act of observation merely records a pre-existing property of a system. Schrödinger's experiments revealed that, in the quantum domain, observation may play a more active role, influencing outcomes in ways that challenge classical assumptions. The idea that the observer cannot be entirely separated from the observed remains central to discussions in quantum theory. Schrödinger's work forced scientists to confront uncomfortable questions about the relationship between consciousness, information, and physical systems, laying the groundwork for ongoing research in quantum information theory and the foundations of physics. Schrödinger's willingness to confront paradoxes also exemplifies his broader philosophical courage. Many scientists prefer models that are convenient, internally consistent, and easily applied to experiments. Schrödinger, however, embraced the contradictions inherent in quantum theory, recognizing that these anomalies were not weaknesses, but windows into deeper truths. His thought experiments encouraged a culture of critical inquiry, challenging physicists to think beyond conventional frameworks and question the assumptions underlying their interpretations. By doing so, Schrödinger not only advanced the technical understanding of quantum mechanics, but also shaped the intellectual culture of the field, emphasizing the importance of conceptual clarity and philosophical reflection alongside mathematical precision. Another profound consequence of Schrödinger's work is the way it bridges microcosmic phenomena with macroscopic intuition. Quantum mechanics often produces results that defy everyday experience, and the disconnect between microscopic theory and macroscopic perception has long been a source of confusion. Schrödinger's experiments, by placing quantum events in hypothetical scenarios involving everyday objects, created a bridge between the scales. They allow us to contemplate the strange consequences of quantum mechanics in familiar terms, providing insight into the limits of classical reasoning. This scaling of thought, from abstract equations to conceptualized macroscopic systems, exemplifies the unique power of his approach. The influence of Schrödinger's conceptual probing extends beyond his immediate contributions to quantum mechanics. His methodology inspired generations of physicists to employ thought experiments as a means of exploring theoretical possibilities. From Einstein's consideration of light quanta to modern explorations of entanglement and decoherence, thought experiments have become a standard tool for testing the logical consistency of theories and exposing underlying assumptions. Schrödinger's work established that imagination, guided by rigor, is not secondary to empirical science, but an integral component of it. His bold questioning demonstrated that the human mind can extend the reach of experiment and reveal insights about reality even in the absence of physical observation. Schrödinger's approach also challenged the conventional boundaries between science and philosophy. By interrogating the implications of quantum theory, he raised questions about determinism, causality, and the nature of existence. These questions are not purely speculative, they inform the interpretation of experimental results and guide the development of theoretical models. Schrödinger's thought experiments illustrate that physics is not simply about calculations, but about understanding what the equations mean in terms of the fabric of reality. This blending of technical analysis with philosophical inquiry enriched the scientific discourse and demonstrated the value of interdisciplinary thinking in addressing foundational questions. The paradoxes he highlighted also underscored the importance of coherence in theoretical models. Schrödinger was acutely aware that quantum mechanics, while highly successful in predicting outcomes, could produce logically inconsistent or counterintuitive scenarios if interpreted without care. By using thought experiments to expose these potential inconsistencies, he forced physicists to refine their understanding of the formalism and its implications. The rigorous interrogation of theory through imaginative scenarios became a hallmark of the field, influencing how physicists approach the development of models and the interpretation of experimental data. Schrödinger's work exemplifies the interplay between theory, intuition, and conceptual exploration in advancing scientific knowledge. Schrödinger's intellectual courage is further evident in his willingness to question the completeness of existing theories. His experiments raised the possibility that quantum mechanics might not fully describe reality, or that additional principles could be required to reconcile theory with observation. This questioning prompted discussions about hidden variables, alternative interpretations, and the role of consciousness in measurement. Schrödinger's insistence on examining the conceptual foundations of quantum theory ensured that the field remained dynamic and open to critical analysis, fostering a culture in which questioning and skepticism are valued as essential components of progress. The legacy of Schrödinger's thought experiments also lies in their pedagogical impact. By transforming complex quantum concepts into vivid scenarios, he enabled students and researchers to grasp ideas that might otherwise remain abstract and inaccessible. The cat paradox, for instance, remains a staple of physics education, illustrating superposition, measurement, and entanglement in an intuitively engaging manner. This ability to communicate profound scientific ideas through imaginative constructs has ensured that Schrödinger's influence extends beyond research laboratories into classrooms and public understanding, shaping how generations of learners conceptualize quantum reality. Moreover, Schrödinger's work illustrates the essential role of paradox in scientific advancement. By presenting scenarios that appear contradictory or impossible, he forced the scientific community to confront the limits of intuition and classical reasoning. Paradox becomes a tool for clarifying assumptions, testing logic, and stimulating inquiry. Schrödinger's thought experiments demonstrate that progress often arises from engaging with the counterintuitive, from using imagination to uncover inconsistencies, and from rigorously exploring the implications of theory. This methodological insight continues to influence research in quantum foundations, philosophy of science, and theoretical physics. The implications of his questioning extend to contemporary research in quantum information and technology. Experiments in quantum entanglement, superposition, and coherence often directly address the paradoxes Schrödinger highlighted. His conceptual probing provides a framework for understanding phenomena such as qubit behavior in quantum computers, the measurement problem, and decoherence. By exposing the conceptual challenges inherent in quantum mechanics, Schrödinger laid the groundwork for practical and theoretical investigations that continue to shape the frontier of modern physics. The scenarios he imagined remain a source of insight, guiding both experimental design and theoretical interpretation. Schrödinger's approach also reflects a profound humility before nature. He recognized that the universe does not conform to human intuition, and he was willing to entertain scenarios that seemed absurd precisely because they revealed the limits of understanding. This intellectual openness, coupled with analytical rigor, characterizes his contribution to science. He demonstrated that embracing uncertainty and confronting paradoxes are not signs of weakness, but essential strategies for advancing knowledge. Schrödinger's methodology exemplifies the combination of courage, creativity, and discipline necessary to explore the frontiers of understanding. Finally, Schrödinger's bold questioning demonstrates the enduring importance of conceptual clarity in science. While experiments and equations provide empirical verification, thought experiments reveal the deeper meaning of theoretical constructs. Schrödinger's imaginative probes into the nature of reality challenge scientists to consider not just how systems behave, but what it means for them to exist, be measured, and interact. His work ensures that quantum mechanics is not only a technical tool, but also a framework for understanding the profound and sometimes unsettling implications of the microscopic world. By daring to question reality itself, Schrödinger expanded the boundaries of human knowledge and left a legacy that continues to inspire, challenge, and illuminate the deepest questions of existence. Erwin Schrödinger's exploration of the nature of life represents one of the most remarkable intersections of physics and biology, a journey that transcended disciplinary boundaries and reshaped how scientists conceive living systems. While he is best known for his groundbreaking work in quantum mechanics, Schrödinger turned his attention to biology in the mid-20th century, seeking to understand how physical laws could explain the astonishing order and stability found in living organisms. At the time, biology was largely descriptive, focused on cataloging species, structures, and processes, but lacked a theoretical framework that could connect the phenomena of life to the principles of physics. Schrödinger approached this challenge with the mindset of a physicist, asking questions that were both audacious and deeply insightful. How can molecules carry the information necessary for life, and what mechanisms preserve the stability of complex biological systems over time? In his seminal work, Schrödinger introduced the concept of an periodic crystal to explain the storage of genetic information. He argued that hereditary material must possess a highly ordered yet flexible structure, capable of encoding vast amounts of information while remaining resilient to environmental fluctuations. This idea anticipated the discovery of DNA and the double helix decades later, providing a conceptual bridge between physical principles and biological function. Schrödinger's reasoning demonstrated that the laws of physics, including quantum mechanics and thermodynamics, could account for the precision, efficiency, and reproducibility of biological processes. By framing life as a problem of physics, he encouraged a quantitative and analytical approach to biology, inspiring researchers to seek molecular explanations for phenomena that had previously been understood only qualitatively. Schrödinger's contributions also emphasized the interplay between order and disorder in living systems. He introduced the notion that organisms maintain their structure and function by feeding on negative entropy, a concept that highlighted the dynamic balance between energy consumption and organizational stability. This perspective was revolutionary, suggesting that life is not exempt from the laws of physics, but instead exploits them to sustain complexity. By framing metabolism, reproduction, and adaptation in terms of energy flow and statistical mechanics, Schrödinger provided a framework for understanding how living systems resist decay and maintain information over time. His ideas foreshadowed the development of molecular biology and systems biology, fields that now routinely use physical principles to explain biological phenomena. Furthermore, Schrödinger's approach bridged the gap between microscopic and macroscopic perspectives. He recognized that processes at the atomic and molecular level underpin the stability and behavior of entire organisms. By applying quantum mechanics to biological questions, he opened the door to understanding enzyme function, genetic replication, and the mechanisms of heredity with unprecedented depth. His work emphasized that the mysteries of life are ultimately compatible with the laws governing inanimate matter, challenging the notion that biology operates under separate or exceptional rules. In doing so, Schrödinger set the stage for the integration of physics and biology, fostering interdisciplinary inquiry that has since become foundational to modern science. Perhaps most importantly, Schrödinger inspired a generation of scientists to think boldly about the unknown. His writings conveyed both rigor and wonder, demonstrating that the study of life could benefit from the same analytical precision used in physics, while also embracing the complexity and subtlety inherent in biological systems. By framing life as a physical problem, he shifted scientific thinking from purely descriptive observations to mechanistic understanding, ultimately influencing the discovery of the molecular basis of heredity and the rise of molecular biology. Schrödinger's contributions remind us that profound insights often emerge at the intersection of disciplines, where imagination, curiosity, and analytical reasoning converge to illuminate the deepest questions of existence. Erwin Schrödinger's philosophical reflections on science and reality reveal a dimension of his genius that extends beyond equations and laboratory discoveries. While he is celebrated for his technical contributions to quantum mechanics and the wave equation, Schrödinger also sought to understand the deeper meaning of the scientific endeavor, probing the nature of knowledge, observation, and existence itself. Unlike many of his contemporaries who confined their work to technical precision, Schrödinger recognized that scientific theories carry profound implications for how humans interpret reality. He was not content with knowing that equations could predict outcomes. He wanted to grasp what those predictions meant about the structure of the universe and the place of consciousness within it. His reflections bridged physics, philosophy, and even Eastern thought, highlighting his unique ability to blend rigorous analysis with profound contemplation. Central to Schrödinger's philosophical perspective was the recognition that classical concepts of reality are insufficient at the quantum level. Classical physics presents a deterministic universe where objects exist independently of observation, and their properties can be measured with complete certainty. Quantum mechanics, by contrast, suggests a probabilistic reality in which the observer plays an essential role. Schrödinger was acutely aware of the paradoxes this creates and sought to interpret their implications thoughtfully. He questioned the meaning of measurement, the relationship between mind and matter, and the nature of causality. Through his writings, he encouraged scientists to reflect not only on the technical predictions of theory, but also on the conceptual frameworks that underlie them. In this way, Schrödinger helped cultivate a deeper, more reflective approach to understanding the world. Another important aspect of Schrödinger's reflections is his emphasis on the unity of knowledge. He believed that disciplines should not exist in isolation. Physics, biology, and philosophy, he argued, are all interconnected in the quest to understand reality. This perspective is evident in his writings on life, where he applied principles of physics to biological phenomena, and in his engagement with questions of consciousness and perception. Schrödinger viewed scientific inquiry as part of a broader intellectual exploration, one that encompasses not only the measurable but also the experiential, subjective aspects of existence. His work demonstrates that scientific understanding is most powerful when it is informed by philosophical reflection, and that philosophical inquiry gains clarity when grounded in empirical knowledge. Schrödinger also grappled with the implications of quantum theory for human understanding. He recognized that the probabilistic nature of reality challenges intuitive notions of causality and determinism. For Schrödinger, this was not a limitation but an opportunity to explore the richness and complexity of the universe. He encouraged an openness to uncertainty, advocating for a perspective in which the universe is seen as dynamic, interconnected, and sometimes paradoxical. His philosophical reflections highlight the idea that science is not merely a tool for prediction, but a means of expanding human perception, deepening our appreciation of the subtle patterns and structures underlying reality. Furthermore, Schrödinger drew inspiration from philosophical traditions outside the Western scientific canon, particularly Eastern thought, including ideas from Vedanta and other mystical traditions. He found parallels between the unity of consciousness described in these philosophies and the interconnectedness implied by quantum mechanics. These reflections led him to consider that the apparent dualities and paradoxes of quantum physics may point to a deeper, underlying coherence in reality. Schrödinger's philosophical inquiries thus extend the implications of his scientific work, suggesting that the study of matter, energy, and life is inseparable from the quest to understand consciousness, perception, and existence itself. His reflections also had a profound influence on the scientific community, inspiring thinkers to consider the broader significance of their work. Schrödinger's writings emphasized the importance of intellectual humility, cautioning against overconfidence in simple interpretations of complex phenomena. He encouraged scientists to confront uncertainty, question assumptions, and remain open to perspectives that challenge conventional thinking. This philosophical mindset complements technical expertise, fostering an approach to science that values both precision and contemplation. Finally, Schrödinger's philosophical contributions underscore the enduring relevance of his thought. By connecting scientific discovery with reflection on reality, he demonstrated that understanding the universe requires not only calculation and observation, but also deep conceptual analysis. His work invites scientists and philosophers alike to explore the implications of their knowledge, to consider the nature of consciousness, and to recognize the profound interconnectedness of all aspects of existence. In doing so, Schrödinger transcended disciplinary boundaries, leaving a legacy that continues to inspire inquiry at the intersection of science, philosophy, and the human quest for understanding. Erwin Schrödinger's influence on modern quantum mechanics and physics is profound, enduring, and multifaceted, shaping both theoretical frameworks and practical applications in ways that continue to resonate across the scientific community. His work, particularly the formulation of the wave equation, provided the foundation for understanding the behavior of particles at the atomic and subatomic levels. By translating the abstract principles of quantum mechanics into a mathematically rigorous and conceptually coherent framework, Schrödinger enabled physicists to explore the microscopic world with unprecedented precision. His insights not only resolved critical problems in atomic theory, but also set the stage for a revolution in physics, establishing principles that underpin much of modern scientific research. One of the most immediate impacts of Schrödinger's contributions was the formalization of wave mechanics as a central pillar of quantum theory. Prior to his work, the field was dominated by matrix mechanics which, although powerful, lacked the intuitive clarity and spatial visualization provided by wave mechanics. Schrödinger's formulation allowed scientists to model particles as wave functions, providing a clear depiction of probability distributions and dynamic behavior. This approach offered a unified framework for understanding a wide variety of quantum phenomena, from the energy levels of hydrogen to the interactions of complex molecules. The elegance and generality of his equations facilitated rapid adoption by the scientific community and provided a foundation for ongoing theoretical development. Schrödinger's influence extends beyond wave mechanics itself. His work helped establish the conceptual underpinnings of quantum theory, emphasizing the probabilistic nature of particle behavior and the central role of measurement. By demonstrating how the wave function evolves over time, he provided a powerful tool for predicting experimental outcomes while highlighting the limitations of classical deterministic thinking. This perspective reshaped the way physicists approached the microscopic world, fostering a mindset in which uncertainty and probability were not obstacles but intrinsic properties of nature. Schrödinger's contributions thus helped define the philosophical as well as the technical framework of modern quantum mechanics. The practical implications of Schrödinger's work are equally profound. Wave mechanics has become essential in fields such as quantum chemistry, condensed matter physics, and atomic and molecular physics. By enabling precise calculations of electron configurations, molecular interactions, and energy states, Schrödinger's methods underpin technologies ranging from semiconductors and lasers to nuclear energy and advanced spectroscopy. His work has guided experimental research, allowing scientists to predict and verify phenomena that were previously inaccessible. In this sense, Schrödinger's influence is not purely theoretical, it has tangible consequences for both scientific inquiry and technological innovation. Schrödinger's conceptual innovations also shaped the interpretation and teaching of quantum mechanics. The clarity of his approach provided students and researchers with an accessible yet rigorous framework for exploring complex phenomena. Wave mechanics became a cornerstone of physics education, forming the basis for understanding atomic structure, molecular bonding, and the behavior of matter at quantum scales. Schrödinger's contributions ensured that the next generations of physicists could build upon a coherent and robust foundation, facilitating advances in research and innovation across multiple disciplines. Moreover, Schrödinger's influence extends to the philosophical discourse surrounding quantum mechanics. His thought experiments, such as the famous cat paradox, forced scientists to confront the implications of superposition, measurement, and observation, stimulating debates about the nature of reality and the limits of human knowledge. These reflections continue to shape contemporary discussions in quantum foundations, influencing interpretations ranging from Copenhagen to many worlds theory. Schrödinger's work demonstrates that the impact of scientific discovery is not confined to equations alone. It also shapes conceptual understanding and inspires ongoing inquiry. The legacy of Schrödinger's influence can also be seen in emerging fields such as quantum computing and quantum information theory. Principles derived from his wave mechanics, particularly superposition and probability amplitudes, are foundational for designing qubits, understanding entanglement, and developing algorithms that exploit quantum behavior. Schrödinger's vision of particles as wave-like entities capable of existing in multiple states simultaneously has direct implications for the technology of the future, illustrating the enduring relevance of his insights. Finally, Schrödinger's contributions exemplify the integration of mathematical precision, conceptual clarity, and imaginative thinking that defines revolutionary science. His work not only solved critical problems of his time, but also established the intellectual framework that continues to guide research in quantum mechanics and physics more broadly. From the fundamental understanding of atomic and molecular behavior to the philosophical contemplation of reality, Schrödinger's influence permeates both the practical and theoretical domains of modern science, ensuring that his legacy remains central to the ongoing exploration of the quantum world. Erwin Schrödinger's enduring legacy lies not only in his groundbreaking contributions to quantum mechanics, but also in the profound influence he exerted on the way science is conceptualized, taught, and philosophically interpreted. Schrödinger's work continues to shape the intellectual landscape, bridging the realms of mathematics, physics, biology, and philosophy. His influence is felt in both the practical applications of modern technology and the ongoing debates surrounding the nature of reality, consciousness, and the structure of the universe. Few scientists have left such a multidimensional imprint, where theoretical insights resonate across disciplines and inspire generations of thinkers to question, explore, and innovate. At the core of Schrödinger's legacy is the formulation of the wave equation, a discovery that transformed the understanding of the microscopic world. By providing a coherent mathematical framework for describing the probabilistic behavior of particles, Schrödinger offered a tool that has become indispensable in quantum mechanics. His wave mechanics allowed scientists to calculate atomic and molecular properties with precision, bridging theoretical predictions and experimental observations. This framework not only solved critical problems in physics, but also opened the door to innovations in chemistry, materials science, and emerging fields like quantum computing. The predictive power of his equations and the conceptual clarity they provide ensure that Schrödinger's contributions remain central to scientific research nearly a century later. Beyond the technical achievements, Schrödinger's enduring influence is evident in his capacity to integrate philosophy with scientific inquiry. He recognized that quantum mechanics raises questions that extend beyond mathematics and laboratory experiments, touching upon the very nature of existence, causality, and observation. Through his thought experiments, he challenged scientists to examine the implications of quantum theory, highlighting paradoxes that force a reconsideration of classical assumptions. His reflections on reality, superposition, and the role of the observer continue to inform philosophical debates, influencing perspectives on consciousness, determinism, and the limits of human knowledge. Schrödinger's work exemplifies the productive interplay between rigorous science and profound philosophical inquiry, demonstrating that understanding the universe requires both calculation and reflection. Schrödinger's impact on biology further amplifies his legacy. His conceptual approach to life, articulated in his exploration of genetic information and the periodic crystal, inspired the development of molecular biology. By framing heredity and biological stability in terms of physical laws, he provided a conceptual framework that influenced pioneering discoveries in DNA and molecular genetics. Schrödinger's ability to see connections across disciplines, to apply principles of physics to the mysteries of life, exemplifies the breadth of his vision. His work encouraged scientists to adopt interdisciplinary approaches, paving the way for a more integrated understanding of the natural world. Education and scientific culture have also benefited from Schrödinger's influence. His writings, both technical and philosophical, serve as models of clarity, rigor, and intellectual curiosity. He inspired generations of students and researchers to think critically, embrace uncertainty, and confront paradoxes rather than shy away from them. By demonstrating that imagination and creativity are integral to scientific discovery, Schrödinger helped cultivate an intellectual environment in which bold ideas and conceptual exploration are valued alongside technical proficiency. His legacy thus extends not only through discoveries, but also through the mindset he fostered in the scientific community. Technological applications stemming from Schrödinger's contributions further cement his enduring impact. Wave mechanics underpins quantum chemistry, semiconductor design, and the development of lasers and advanced materials. His insights into probability, superposition, and the behavior of particles are essential to the ongoing development of quantum information technologies and quantum computing. In this sense, Schrödinger's work continues to influence both theoretical research and practical innovation, shaping the tools and technologies that define the modern scientific era. Ultimately, Schrödinger's legacy is characterized by the integration of precision, imagination, and philosophical depth. He demonstrated that science is not merely the pursuit of equations or measurements, but a quest to understand reality in its most profound dimensions. His contributions continue to guide research, inspire inquiry, and provoke reflection across disciplines. Schrödinger's work stands as a testament to the transformative power of curiosity, intellect, and the courage to question assumptions, ensuring that his influence endures not only in physics and biology, but in the broader human quest for knowledge and understanding.